Are you looking to learn networking for cloud computing? If so, this video is for you. Hi, my name is Michael Gibbs and I'm the founder and CEO of Go Cloud Architects, and we're an organization dedicated towards building high-performance cloud computing careers. I've been working in technology for over 25 years, and I've been coaching and mentoring others for 2 decades. And networking for cloud computing, or even networking in general, is one of my favorite topics to talk about because I've been doing this for so long. In fact, I'm one of the original Cisco certified internet experts, and my CCIE number is 7417, so that can tell you how long I've actually been working in networking. So the agenda for today's discussion is what is networking. Then we're going to talk about the OSI model, then we'll talk about the TCPIP protocol stack, and then we'll talk about LANs and WANs. We'll talk about what is a router and how does it work. We'll talk about what is a switch and how does it work, and we'll cover VLANs and trunking. And again, this is just a basic introduction to networking, but it's networking training for cloud computing. So let's begin with the definition of what is networking. And networking simply is just connecting all of your systems so they can talk to each other. Networking is really the plumbing that enables everything to work. I'd like you to think of networking as a system of roads. So for example, if you got in your car and you wanted to drive to your friend's house, you would get in your car, you would go to the road, and you would make the turns that are necessary to get there. And what would you need in order to do that? Obviously, you need the car, but you would also need the roads. The roads are your path. So what do networking devices do? They build a path for your data to get to point A to point B, just like the roads do when you drive your car. But not only is it enough to have the roads, you need to know how to get there. So what routers also do, and network also does, is it determines the best path for your data, because once you send your data, it's got to go through a large path to get to its destination. And that's what networking does. Now there's all kinds of varieties and questions about networking. You hear people talk about load balancers and the concept of networking, but that is not networking. Networking for cloud computing, or networking in general, is routers, switches, cables, LAN, and WAN connections. That's it. That's the entire network. Now, obviously, these routers run routing protocols, which determines the best path of your data to get to the destination, which we'll talk about in another video. And switches also make sure there's redundancy, but they also make sure there's no loops and there's protocols in these devices. But networking is exclusively routers, switches, cables, LAN, and WAN connections. That's the network. So the next thing we're going to talk about now that we've defined a network is the OSI model. The OSI model, or Open Systems Interconnect model, was a model designed to basically make all of us understand the 7 layers of communication that actually go on inside of an organization and their applications. It's fundamental to the design of systems. It's fundamental to your knowledge for troubleshooting of systems, so you must know the OSI model. So it's a 7-layer model, and there's going to be 7 layers which we're going to talk about. Layer 1 is physical, layer 2 is data link, layer 3 is network, layer 4 is transport, layer 5 is session, layer 6 is presentation, and layer 7 is the application layer. Now we're going to define each one of these layers. Layer 1, or the physical layer, is really the media that gets your data from point A to point B. So it's your cabling. It could be a wire, it could be a fiber optic cable, but it's still a cable. And at this layer, we're realistically speaking with, either light or electrons, but what we're transmitting is bits. That's the physical layer. Now, at the second layer, or the data link layer, this is the hardware layer. So for example, if your computer has an Ethernet card, that is the way it connects to the network. And the Ethernet card itself is a layer 2 device, and it has a physical or a hardware address on that, and that's called the MAC address. So we used to have lots of different data link layers. Today it's traditionally mostly Ethernet, and when we're dealing with Ethernet, it's got a hardware address, and that hardware address is referred to as a MAC address. Now when we send data at layer 2, we're sending what's called frames. Now the next layer up is the network layer, and this is a logical addressing layer. This is the routing layer. So layer 3 is determining the addresses, and it also determines the path to get your data through the network from point A to point B. And at layer 3, we're using IP addresses, for example. And at layer 3, we're sending packets. So layer 1 is bits, layer 2 is frames, layer 3 is packets. So these 3 are very fundamental layers to networking, and the next layer, or layer 4, is the last realistic fundamental layer when you're dealing with networking. And that's the transport layer. And the transport layer basically determines your end-to-end connections and how that's going to work. And this is where you'd be using something like TCP or UDP or ICMP, and we'll talk more about that in a minute, but we're sending segments at this layer. So layer 1 is bits, layer 2 is frames, layer 3 is packets, and layer 4 is segments. Now layer 5 and above is not really part of networking per se, but we're going to cover them anyway. Layer 5, or the session layer, is really related to inter-host communication, and we're talking about sockets and things like that. Layer 6, or the presentation layer, is really about taking the data that came up from the previous layers and presenting it to the application layer, which is where the users use things. But encryption also happens at this layer too, so think of layer 6, the presentation layer, as a place where you're going to do your TLS encryption, for example. And then layer 7 is the application layer, so your web browser or any applications that you write. For example, think of things like HTTP, HTTPS, SSH, DNS. This is a layer 7 because it's an application. So layer 1, physical, bits. Layer 2, data link, MAC addresses and frames. Layer 3, network, think IP addresses and packets. Layer 4, think TCP, UDP, ICMP, and we're dealing with segments. So let's talk about the TCPIP protocol stack, which is comprised of realistically three transport protocols. And they're going to be TCP, UDP, and ICMP, and we're going to talk about the use case for each. So inside of this, we have a means to test the network with ICMP, to do reliable network transfers with TCP, and to do real-time transfers with UDP. And we're going to talk about how each one of these works. If I needed to send you something really important, say I took a whole bunch of photos of my family and I thought it was important, I wanted you to send these photos in perfect condition and make sure the photo that I sent you and the photo you receive are 100% identical, I must use TCP. And the way TCP works is I do the following. I establish a connection with you, for example. So the first thing I do is I open up a connection with something called the SYN, but that's a little more than we're in detail we're going to get here. And then you see my SYN and you say, okay, I got it. I agree to open up a connection to me. So you send an acknowledgement and a SYN to me. And then we establish a bi-directional relationship. So we've already agreed to talk to each other. Now at this point, what would happen is I'd send you a piece of data and you'd say, I got it. And I'd say, okay, good. If you got that one piece of data, I sent you 2 pieces of data. And you say, I got it, Mike. And I got the message, you've got it back. And then I send you 4 pieces of data. And I'm going to send you as much data as I can before you start to lose data. If you lose data, I'm going to slow it back. I'm going to back off and start again. Send 1 packet, make sure you receive it. Send 2, make sure you receive it. Send 4, make sure you receive it. Send 8, make sure you receive it. And I'm going to do this until I can find the flow of how much data that I can send you that you're going to receive. So TCP is useful for reliable because it guarantees that what you receive and what I send are the same thing. Now, let's say I wanted to do something real time. I wanted to stream a video. We wanted to have a voice over IP conversation. TCP would be a disaster. See, I need to send you as much data as fast as possible, and I need you to receive the data as fast as possible and send it to me as fast as possible. Now, in TCP, I talked about I send you some data, you acknowledge it. I send you more data, you acknowledge it. Could you imagine trying to do that for a voice conversation? Or, what's worse? What if I send you data, you don't receive it, and you ask me to retransmit it? So with TCP, for example, let's say I send you packets 1 through 10, and you acknowledge them. And then I send you 11 through 20, and before I even get the acknowledgement back, I send you 11 through 20, and then some of them make it, but not all of them. And then I send you 20 through 30, and then I retransmit the ones from 11 to 20. Well, now we're going to have messages in all kinds of crazy order. So if I'm trying to say a sentence to you, and the packets arrive out of order, you could have a sentence that's completely meaningless, for example, or a video that's meaningless. So when we're dealing with real-time data, if you lose a little bit of it, it's not great. But if you retransmit or you have out-of-order packets, it's a disaster. So when you have real-time applications where I need to send you data as fast as possible, like voice or video, live voice or video, we're going to use UDP. Now, there's the last part of this protocol stack, which is called ICMP, or Internet Control Message Protocol, and that's really used for network testing. If I want to see if a device is there, I send a ping. If it responds back to me, I know it's there. If I want to determine if the path is good from the source to the destination and I run a trace route, again, it's going to use ICMP and give me information. So ICMP is used to diagnose and discover things and troubleshoot. Now let's talk about how network devices determine how to get their path to their destination. Well, every packet or every layer 3 part of the network that you send has a header. And when you're looking at the header of the IP packets, it basically tells you a lot of things. If you look in the header, for example, you can see the source address, meaning the source address that's sending it, and the destination address. Routers look at the destination address and they forward it to their path. So you can see that right here. You have the protocol in the header, which is TCP, UDP, IDMP, and you have something called the time to live. See, what happens if I was to send data and there was no time to live, my data, even if it didn't get to the destination, would circle the globe again and again and again and again and never stop. So the packets themselves have something called the time to live. And basically every time a packet traverses a router or goes through a router, its time to live is degraded by 1. So if you have a time to live of 10 and you pass 10 routers, the packet is dropped. So the time to live makes sure your packets don't go around forever. Now the next thing you need to really think about from this is you've got something called the DS field. The DS field, what it's really telling you is if you have to prioritize certain traffic, you'd mark it in there. So these are the main things that you need to see in the TCP, in the IP header, the things that you can actually look at, the TCP header. So now let's talk about LANs and WANs. So a LAN, or a local area network, is something that's plugged into your switches that's local. So in your house, you probably have a local area network. You probably have a couple of switches, maybe some routers, and everything plugs in. If you're in the office, there's a closet that's got a whole bunch of switches that are plugged into a router. Again, that's a local area network because it's local to you. So a campus, a data center, and an availability zone, for example, in the cloud is going to be a local area network. Now, a wide area network is something different. A wide area network is when you connect someplace like, say, New York to someplace like San Francisco. It's a long distance. That's why it's called a wide area network. Think of your data center, the cloud, as a wide area network. Think about your direct connections to the cloud, which would be a wide area network. So that's wide area network technology. So let's look at this diagram, which is a conceptual view of a LAN. In this case, we've got 2 buildings, and each building has their own switches and their own routers, and there's basically a piece of fiber optic connection between them. So this is a local area network where we've got 2 buildings that are Site 1 and Site 2, which basically are across a parking lot with some fiber in between them. That's conceptually what a LAN is, or a local area network. You've got your computers plugged into the switches, and you've got your routers also plugged into the switches, and then the routers connect to each other over the network. And that provides your network connectivity. So now we can talk about a WAN, or a wide area network. It's basically just connecting location 1 to location 2. And as you can see in this diagram, what we've really done is we've gotten a fiber Ethernet link on both sides of the connection, because anytime you're going to go, say, above 100 meters, you need to use a fiber optic connection. And if you're going to go from your data center to the service provider's environment, chances are it's going to be longer than 100 meters, and you're going to need a fiber optic connection to get there. So basically, your organizations, you have a connection to the service provider's edge, and then once you get to the service provider's edge, they basically create a pseudo wire or a fake wire, giving you the equivalent of a wire between location 1 and location 2. And as you can see in this environment, it's R1 or router 1 and R2 the router 2, and that's where the WAN connectivity would occur. People get confused by this concept of Ethernet over MPLS. So someone like me that's designed MPLS backbones, MPLS is just another way to switch your traffic across the network, and it requires IP connectivity. So typically what we would do as service providers is we would set up the systems, we would set up our IGP, we'd set up all of our BGP peering, for example. Then we would set up something called RSVP signaling, and we create some traffic engineered tunnels. And then on top of that, what we would do is create a wire, and we'd call it a pseudo wire, and basically we would just tunnel your Ethernet traffic over the wire on both sides. We'd send it from one side to the other side. You would have no idea it's MPLS. All you would know is you've got a wire. So whether you're dealing with an Ethernet WAN or an Ethernet over MPLS WAN, to you as an organization, the effect is the same. It's just a wire you're receiving. So don't let that complexity confuse you. There's other parts of MPLS which can get very complicated, but that's not necessary when you're just purchasing an Ethernet WAN. So we talked about the WAN, the LAN, we talked about the TCPIP protocol stack, we talked about the OSI model. Let's talk about the network devices. So let's start with a router. What is a router? A router is effectively a server with a whole lot of network interfaces, so at its most elemental level. So let's say you've got a computer that has 2 network cards. Network card 1, which is my left arm, and network card 2, which is my right arm, although it may look different on the camera. I know as a router that if I need to reach a certain destination, I either have it in the map for my left arm or have it in the map for my right arm. And I send the data about the right interface to get it closer to its destination. So routers basically route or help packets get from point A to point B. And how does this work? Routers build a map of the network. And the map basically says, To reach destination, use this link. To reach this destination, use this link. And they build the map. Now, the way they build the map, which is called a routing table, is routers typically have what's called a routing protocol. And each one of these routers exchanges information, and they tell each other which subnets they have and which links they have. And that's how the routers know how to get your data to this destination. Now, that's called dynamic routing, and that's the way you would set up a network that's got more than one or two routers, because you don't want to be trying to put routes on thousands and thousands of routers. And you also want your network to be self-healing. So when organizations use dynamic routing through a routing protocol, if a link breaks and there's multiple redundant links, the routers can still get your data from point A to point B. So that's why organizations use dynamic routing. Now, you can also configure static routes, which is where you basically tell the router, okay, to reach this destination, click this link. Now, your PC, for example, will have a static route on it, and that'll be the default gateway, which basically says, if you don't know how to send your data anywhere, send it to the default gateway, which is a router, and then the router will know what to do with it. So now you know the concept of what a router is and how it builds the map of the network. Now let's look at this routing thing in action. So let's say you're PC1 that desires to reach PC2. And in this environment, PC1 says, I need to reach PC2. So either through DNS or some other means like a host table, the PC says, I know how to reach PC2. Its IP address is XYZ, what have you. So then PC1 says, I need to get my data to PC2. I'm going to then say, how do I get my data there? So PC1 is going to say, I don't have a route, but I do have a default route which says go to router 1. So PC will send its traffic to router 1 because that's its default gateway. Now, when it gets to router 1 will say, I actually have a path to the subnet where PC2 is. Let me send my data to the next hop. And router 1 will then say, send it to router 2, because router 2 told router 1 that it has a path to the subnet where PC2 is. Now at this point, when the packet's there, the router 2 sends what's called an ARP message or a broadcast message, which says, who has the MAC address for PC2? PC2 will respond, and then PC2 will be able to communicate or receive the message that was sent by PC1. Now PC2 is going to say, I have to reply to this message. Thank you for requesting this content. Now PC2 is going to say, I don't have a route to PC1, but I have a default gateway. Let me point it to router 2. So it's going to send its data or its packet to router 2. Now router 2 is going to say, I don't know the IP address of PC1, but I have a route to the subnet through router 1. So let me send my data to router 1. Now, when the message gets back to router 1 from PC2, router 1 is going to say, I have that subnet. It's locally connected. Let me send an ARP, a broadcast message, to see who has that MAC address. And then after that occurs, and PC1 replies to PC2, now you have the ability of bidirectional communication, and that's how your data goes from point A to point B. That's routing completely simplified. So now let's talk about what is a switch. Since a router was a layer 3 device, what is a switch? Well, a switch is a layer 2 device. Typically speaking. Now we also have layer 3 switches which integrate switching and routing in the same device, but when we talk about switching, we're talking about layer 2. Think frames, think MAC addresses. Now let's discuss what is a switch. A switch is a layer 2 device, and a switch is where all your things are plugged into. Where do you plug in your servers? Where do you plug in your workstation? Where do you plug in your routers? They all get plugged into a switch. So a switch is the place with all the ports. And actually switches will even plug into other switches, and you'll even be plugging your physical load balancers into a switch. So a switch is where everything gets plugged into. Now because switches are a layer 2 device, they function based upon layer 2 things, which means they forward frames. See, routers forward packets and switch forward frames. The way switches work is basically, if an unknown frame comes into its system, it floods it out all ports of the switch until one of the users responds and says, I am the user for that frame. And then that user will respond and the switch will build a table. So a switch is going to build a table of MAC addresses. And once the switch knows which port a host is, traffic destined for that host will only go out that one port. So switches really improve network performance compared to what we used to use many years ago called a hub, because in switches, you know exactly where to send your traffic. And there's also separate broadcast domains. They're all in a broadcast domain, but each port is a separate collision domain that is way beyond the scope of what we need to talk about here. But just understand that switches build a table and they will forward frames out the port where the host is when they know. But if they don't know, a switch will forward frames out every single port except for the one it came in on. So switches build a table just like routers. Switches are intelligent devices that build a MAC address table and know how to send data out only to the port on the switch where it's intended after it builds this table. Now, because we're talking about switches and we're also talking about the cloud, let's talk about a concept of switches, and specifically virtualization. So we have virtualized servers and we have virtualized switches. It's the same concept. So many years ago, we started looking at the concept. Let's say we had 100 ports in the switch. And we said they could all speak to each other. They're all on something called a broadcast domain, which means everybody could see everybody's broadcast traffic. And what if you didn't want users to talk to each other? What if you wanted to keep HR separate from finance, which was separate from dev, which was separate from test? You might want to do that. How could you do that? Well, you could have 4 separate switches. That would work. Or you could basically take a switch and divide its port up into multiple logical virtual switches called virtual LANs. So in this environment, we've drawn a diagram which you can see, and I've created 4 virtualized LANs on the switch on the left and 4 virtual LANs on the switch to the right. Virtual LAN A and virtual LAN B and virtual LAN C and virtual LAN D, they are all separate, all on the same switch. So ports 1 through 24 and this particular switch are part of VLAN A. And ports 24 through ports 25 through 49 are parts of VLAN B, and ports 50 to 74 are VLAN C, and ports 75 to ports 100 are VLAN D, and that's how I've configured the switch. And that's the way it's all set up. And I've done the same thing on both sides. So now on both sides, we've got 4 virtualized switches in each switch. Now, that's how it works. That's what all VLAN is you're taking a switch and you're chopping it up into multiple virtual switches. Now, let's say now you wanted to have VLAN users in different parts of your campus, because this happens all the time. Let's say you've got accounting users in one building, but you also have accounting users in another building. Then what you would need to do is you'd need to connect them. So looking at this architectural example in this picture, you could easily run a cable from VLAN A to VLAN A, and VLAN B to VLAN B, and VLAN C to VLAN C, and VLAN D to VLAN D, and you would have full connections between all the VLANs, and complete and total security. Because you've got a cable between VLAN A and VLAN A, only VLAN A and A could talk to each other. Same thing for VLAN B, it would work perfectly. And this is one of the ways organizations could do their cabling. Now, what if an organization wanted to do something more efficient? What if they wanted to send all their traffic across a cable or a bundle of cables? They could do something called trunking, and trunking is extremely important networking for cloud computing, and we'll tell you why in a minute. How would this work? A trunk port is a port that could say you've got a port between two switches where you can carry multiple VLANs traffic. But you need to keep the VLANs traffic isolated, and you need to keep the VLANs traffic separate, so for security purposes. So what you would do is when you put your frame on the wire, you would add a tag that would identify your traffic and separate it from everyone else. So when you do VLAN trunking in today's modern world, you're putting what's called an 802.1q tag on it. So when you're trunking between things, the trunk port will look for the 802.1q tag, which will be different for VLAN A versus VLAN B versus VLAN C versus VLAN D. So what will happen is the switch will tag it, and then it will take it across the wire, and then the receiving switch will pull the tags off and send the data, meaning the frame, to its ultimate destination VLAN. And that's how VLAN tagging works. Now let's take about this from a cloud computing environment. If you're going to get a direct connection to the cloud, you're going to have to send it to them on a VLAN with a .1q tag. Why? Because AWS is then going to keep your traffic separated on a layer 2 network when it gets backhauled to their systems. So VLANs and tags are critical knowledge for cloud computing. So in today's discussion, what did we talk about? We talked about what is networking. We talked about the OSI model. We talked about the TCPIP protocol stack. We talked about local area networks and wide area networks. We talked about what is a router and how does it work. We talked about what is a switch and how does it work, and we did an introduction to VLANs and trunking. I hope you've enjoyed the content of today's networking for cloud computing. Now let's talk about some 3 things that we do for the Cloud Architect community here at Go Cloud Architects. On every Monday and every Thursday, we have a completely free How to Get Your First Cloud Architect Job webinar. On these webinars, we will teach you everything that you need to know to get your first cloud architect job. We will teach you what you need to learn, what you need to study, things to do. In terms of labs, we will tell you what needs to be on your resume, the kind of experience to get, and how to interview, and what hiring managers desire. It's something we do free for the Cloud Architect community every Monday and every Thursday. Now, on almost all Tuesdays, we have a Cloud Architect Experience webinar, and on these webinars, we have a lot of fun. We will teach you how to get cloud architect experience, the kind that employers desire, and we usually present you, if we have a big enough group, which we almost always do, with a cloud architect challenge. We will give you a technology situation coming from a CIO, and what you will then do is you will design the architecture on multiple clouds with the people on the call, and you will learn what it's like to work as a real-life cloud architect, and we do that as part of our cloud architect training, and we do that completely free every Tuesday. Now, we care so much about this cloud architect community, and we work so hard to help people get their first cloud architect job, that on every Wednesday we have a free YouTube Live, or at least most Wednesdays, and you can bring us any cloud architect career questions, and we will answer your cloud architect career questions in real time. We do this as a free service because we know if you know how to get to your destination, you'll get there a lot quicker and be more likely to succeed. And we want to do everything we can to help the cloud architect career community. Now let me tell you about some other free training options we have. We have a completely free AWS Certified Solution Architect Associate ebook and full free AWS Certified Solution Architect Associate e-course. I'll leave the links to both in the description below. And we have just created a completely free AWS Certified Solutions Architect Professional Bootcamp. We've been running it on YouTube Live, and it's basically 3 hours a day for multiple days. And on this, we walk you through a complete and total Certified Solution Architect Professional Bootcamp, and we do it in a format where it's basically 40 minutes of lecture and 20 minutes of questions per hour. So chances are the questions people ask might be the questions that other people have. So it's a great full classroom-like experience. Again, it's completely free. I'll leave the link in the description below. Thank you so much for watching this video. I'm honored and privileged and blessed to be part of this cloud architect community. I don't take it lightly, and I try to work very hard with my team to make sure we provide very free, high quality cloud computing training videos on our YouTube channel. Thank you so much for watching this video, and I look forward to seeing you in another video very soon. Take care.